So far, our treatment of defining various parameters in information theory, such as entropy, mutual information, and channel capacity, was with respect to discrete memoryless channel. Okay, so we have seen that for a discrete random variable, okay, the source emitted some message symbols which were discrete random variables, and we had called them as set of x, which took the values x1 x2 up to some specific quantities up to xn with respective probabilities as p of x1 we indicated with capital P to represent probability, and so on up to probability of xn, right? So with this discrete random variable set of all these symbols along with their respective probabilities, we defined the entropy of such source as h of x, which we defined it as summation I from 1 to n p of xi times log of 1 over p of xi, right? So now we'll extend the same definitions, the similar definitions of entropy, mutual information, the conditional entropy, which actually gives the definition of mutual information, and finally with the channel capacity for analog data. Okay, for analog data, we have continuous random variables. Okay, so this we need to deal with continuous random variables. Therefore, we must extend the definition of entropy to such case as well. Okay. We have to define, first we need to define the entropy, which is the starting point to on the way to define channel capacity. Okay, so the road leads to the discussion, including this session for a couple of sessions, including this, would lead to the definition of channel capacity for continuous memoryless channel. But prior to that, we need to define starting from entropy itself. Okay, so in case of analog data, so let's try to define the entropy in this session. Okay, all right. So for a random variable, in case of analog data, which is continuous in nature, a random variable here takes, okay, I can say random variable x takes a value in the range. It takes, okay, takes value in the range. Okay, for a continuous data, we can define that range would be n times delta x, and between n times delta x and n plus 1 delta x. Okay, where n represents the timestamp that we are considering. So a sample value between n times delta x and n plus 1 delta x would be a random value which will fall within this range, and that is true for all n's or any n that we consider. Okay, so this random variable x, it will appear with probability, since we need to know the probability as well to define entropy, which defines the uncertainty. With probability, we can define this as small p times p of n delta x times delta x, where this small p of n delta x indicates this is the probability density function. Check that this is defined with a small p. unlike the probability with capital P. And of course, this delta x is as delta x tends to 0, as this step size delta x tends to 0, as the limit this tends to 0, the error in the approximation will vanish. Okay, because there would be no probability itself, which leads to a fact that there would be no uncertainty. So as delta x tends to 0, as limit as the range diminishes to a single point, then obviously there would be no error involved in defining a particular random variable x. Okay, and hence we can define h of x, the entropy. Therefore, for a continuous random variable, the entropy h of x now can be defined as limit delta x or continuous random variable remains the same. So it's the product of the probability and logarithmic of 1 over probability. Okay, since this is true since it's an average amount of information, the entropy deals with the average amount of information for all the values of n. So we need to take the summation n, and the probability that we have defined just before, which is the probability density function times the step size delta x logarithmic of 1 over the probability. Okay, the same definition that we have defined earlier about the delta x. Okay, this can be further be simplified as limit delta x tends to 0 summation n p n delta x times delta x log, since there are two parts in the product here, so I can split it into two parts. So one will have log of 1 over n p of n delta x minus the second term where I can take the negative term and I can pull this delta x to the numerator, and the rest of the product term summation n p of n delta x times delta x logarithmic of delta x. Okay, I've just replaced log of 1 over ab as log of 1 over a minus log b, okay, which is equivalent to the previous part. Okay, so now plugging limit as delta x tends to 0 inside the summation for a small quantity, and for a large n I can replace this summation with an integration for a continuous data. So that this probability of n times delta x for a very small with probability density function p of x, where x being a random variable, times log of 1 over p of x minus the second term as a limit delta x and log delta x. These are in fact independent of the value n, so I can plug that term outside, say as limit delta x tends to 0. Since delta x is a very small quantity, I can say that this would be log delta x and minus infinity to infinity p of x dx. All right, so this can be simply written as, remember this as limit delta x tends to 0. I cannot just take out the fact of limit delta x tends to 0, because this term involves logarithmic of that small quantity. However, in the first part, we had a density function multiplied by step size, as we can replace such definition of when n is very large and delta x being very small, we can replace with an integration. So of course we applied the same rule even for the second part. However, we can since it's a density function where we have product of n and delta x, that only that term can be replaced with an integration for a continuous variable. All right, but however, we cannot ignore the second part, which is a log delta x, only the part involved here, where we have replaced, to make it more clear. Okay, where we have replaced summation n p of n delta x times delta x, okay, as limit, whereas limit delta x tending to 0, this we have dx. All right, so delta x is retained as simply as dx in the integration part, and we have replaced for a small value of delta x, and for all values of n we have just replaced with an integration for a continuous random variable. All right, so continuing definition of entropy. So therefore h of x is now be written as minus infinity to infinity p of x log of 1 over px minus limit delta x tends to 0 log of simply delta x, where we know that where integration from minus infinity to infinity p of x dx is a probability density function. We know from the definition of the area under the curve of PDF is unity. We can ignore that term. Okay, so as we can see here that, okay, as delta x tends to 0, the log of delta x, we know that this will tend to minus infinity, correct, which is lesser than 1, the logarithmic of that value would be definitely negative. And as delta x tends to 0, this would tend to minus infinity. When the log of delta x tends to minus infinity, this will convert into some finite quantity plus infinity. So all in all, our entropy may seem to be approaching infinity, correct. So that's is the intuition from this result, correct. Associated with the continuous ranges of values. Okay, a continuous random variable, as I said, assumes an uncountable infinite number of values, and hence the uncertainty is also will be in the order of infinity. But does this mean that we cannot define the entropy for a continuous random variable? Can there be any good definition of entropy for a continuous random variable? This needs to be understood properly. Okay, so to define the entropy in a meaningful way for a continuous random variable x, we can consider to define entropy meaningfully. Okay, we can consider this term integration p of x log 1 over p of x as a relative value. Okay, so this is 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 a rela entropy. Mathematically is almost equivalent to a definition of a discrete random variable, where discrete random variable was simply a summation, but the definition was is in in similarly that were defined in earlier cases for discrete random variable. Okay, when we try to compare for continuous random variable, the first part of this seems to be a very similar way. However, we have a second term which is posing a problem. All right, so this can be understood, or entropy can be understood in a more meaningful manner if we consider the first term as a relative entropy, and the second term, which is minus log of delta x term, right, as a reference value. Okay, as a reference. Okay, the information transmitted over a channel that we have defined as mutual information. Okay, so we have defined since mutual information ixy, which is the difference of the source entropy minus the conditional entropy, which is h of x given y. If we define the same reference to define h of x and h of x given y, then definitely the difference of these two quantities will cancel out the reference. Correct? So h of x will also have a reference of minus log delta x. Even h of x given y will also have the same reference of minus log delta x, and the difference of those two quantities will cancel out the reference, and ultimately we'll have a mutual information as we defined for a discrete random process. All right, so the difference, this implies if we have a common reference, the difference will be the same as relative. And for a continuous random variable, remember, we always define the relative entropy but not the absolute entropy, right? So that should be kept in mind. Therefore, for a continuous random variable source, we consider differential, it's a relative quantity, it's a differential entropy, not the absolute entropy the case with discrete random variable. Okay, normally we define, right? So as h of x log 1 is differential. So we can example which is a and is passed through an amplifier. Okay, just take an amplifier where there is some input and certain output. Let us take that the input random variable is x and output random variable is y, which are continuous in nature. Let us say that the gain of this amplifier is 2. Okay, and we'll also say that x will take all continuous values within the range of -1 to 1, and obviously with the gain of 2, with the amplification factor of 2, y will take all the continuous values between -2 to 2, because of the fact that y is twice of x. how will we define the differential entropies of input and output random variables? Okay, what is h of x and h of y? Okay, so to find out these differential entropies or relative entropies, we should know what is the probability. Okay, since it's a uniform distribution function, this has got all the values which we take from -1 to 1 will have uniform, which will have probably say I can say equidistributed between -1 to 1, so that I can define probability of x. So if you try to integrate over -1 to 1, so you'd end up with, since the base here is 2, since the logarithmic base that we have considered all along our definition as binary source, so the this would be simply give us 1 as a value, and as we know the entropy has a unit of bits. Similarly, if we try to find out h of y, which is the entropy, the average amount of information available at the output is -infinity to infinity p of y log 1 over p of y dy. So this exists between -2 to 2, 1 over 4 log 4, which is base 2. This will give us the answer as 2 bits. Okay, so h of x is 1 bit, h of y is 2 bits. Everything is fine, but if you see the fact that but y is simply 2x, as the output of the amplifier is twice of the input. All right, so and we see that the entropy of the random variable y is 1 bit higher than that of x. This means that we are adding an extra information in the amplifier, which results in the amount of information at the output 1 bit higher than the input. Okay, but this is a surprising fact, because that that we know that since a knowledge of x, since it is certain that a knowledge of x determines uniquely a value of y and vice versa, the average uncertainties of x and y should be identical, because amplification itself can neither add nor subtract information. It just amplifies whatever is applied to it. It doesn't add any uncertainty in itself, because we are sure that what is we are going to get at the output, which is twice of the input. So where this extra information that's getting added at the in between the input and output. Okay, that means that h of y is twice as large as h of x. Okay, so this concept becomes clear once we recollect the fact that the entropies that we have defined for continuous random variable is not the absolute entropy, but these are differential entropies or relative entropies. Okay, and if we define R1 and R2 are as the references, okay, for the random variable x and y, for x and y respectively, as delta x and delta y tend to 0, then we can define R1 as limit delta x tends to 0 minus log delta x, and R2 as simply limit delta y tends to 0 minus log delta y. Okay, so the references for each of these entropies are different. Okay, that's the reason we are not getting the entropies at the source and at the output of the amplifier as unequal. So this implies that the difference of these references R1 minus R2 would give me as limit delta x and delta y tends to 0, this would give me log of delta y over delta x. This is nothing but, with the definition of continuous random variable, we can say this is log of dy over dx, and we know that y is equal to 2x, so log of d of 2x over d of x, which will give me, since the base is 2 here, this will give me 1 bit. So this means that R1, the reference entropy of x, okay, R1, which is the reference entropy of x, is higher than, so this implies that R1 is greater than R2 by 1 bit. Since the reference at the source itself is 1 bit greater than the reference at the output, that results in h of y as h of x plus another bit. Okay, otherwise both these entropies are very similar, or the same entropies or same amount of information that we have at the source as well as at the output of the amplifier. Okay, so this means that the entropies that we define for continuous random variable are not the absolute entropies. That should be kept in mind. All right, so similar with respect to discrete random variables, we can find out the maximum entropy, okay, for a continuous channel. Okay, so maximum entropy in case of discrete random variables, we have seen that, okay, all these results are will be essential once we try to define mutual information as well as the channel capacity. That's the reason we need to study all the parameters involved, very similar to that the discussion that we held for discrete random variables. Okay, so for discrete random variables, we observed that maximum entropy, okay, was maximum when it was maximum when all the outcomes or when all the messages were equilikely. Okay, when all the messages are equally likely, or we can say if they are uniformly distributed. Okay, so for continuous random variables, if we try to define maximum entropy for continuous random variable case, okay, so there exists, it's not a probability now, there exists a probability density function p of x, okay, that maximizes the entropy h of x. All right, but in case of continuous random variables, we may have to supply additional information or additional constraints on the random variable x. So it could be either the maximum value of x, or it could be the mean square value of x. Okay, either at the, I can say it could be the random variable, it could be either at the maximum value of x or at the minimum or the mean square value of x. We may get the maximum entropy for a particular probability density function. All right. So we'll try to elaborate on both of these quantities. It can be proved that, but this result is important. It can be shown that these results are available in any of the resources, but I can just take or just pick the final result. So it can be shown that for for p of x is equal to 1 over, shown that for, I'll just continue this, for a given value of, for a given, can say mean square value of x, for a given mean square value of x, let us take that as sigma square. Say for a given value of mean square value, if you try to find out the maximum value of entropy, so that probability density function will have the form of 1 over sigma root 2 pi exponential minus x square over 2 sigma square. So this density function is a very familiar density function which we call as Gaussian distribution. Okay, so therefore I can say that, or we can conclude that for a given mean square value, the maximum entropy or maximum uncertainty is obtained when the distribution x is Gaussian. Okay, for any other distribution function, you would have an entropy less than the maximum. Okay, so therefore, what would be the maximum value of that? Therefore, h of x that we have defined for a continuous random variable as minus infinity to infinity, p of x log 1 over p of x dx. Okay, of course the base is 2. Okay, and log of 1 over p of x, which is logarithmic of 1 over this, which can be written as, okay, which is log of 1 over this quantity, which is log of sigma root 2 pi e power, since it's a negative term, when you take into the numerator 1 over of this would be x square over 2 sigma square, which can be written as logarithmic of 2 pi sigma square exponential x square over 2 sigma square. All right, we can still simplify this part where I can plug the two product terms separately, or we can say I can split this into two parts, where the first part is logarithmic of root 2 pi sigma square, and the second part is simply x square over 2 sigma square log e, okay, where the base is 2 there. All right, so we can still write this as, the root can be taken out and this can be written as simply log of 2 pi sigma square plus x square over 2 sigma square log e. So this is the term, one of the term in the entropy, log 1 over p of x. Therefore, h of x now which is integration minus infinity to infinity p of x times log of 1 over px. Log of 1 over px that we have just written as half log 2 pi sigma square plus x square 2 sigma square log e, right? So we can multiply this p of x into both the terms, and we can pull what is not varying with respect to x, since it's a constant term. So this can be plucked out of the integration log of 2 pi sigma square times minus infinity to infinity p of x dx plus the second term where log e over 2 sigma square is a constant term, and integration minus infinity to infinity p of x, of course this is x square p of x dx. We know that integral the area under the curve of probability density function or probability distribution function is unity, and we can write this as half log of 2 pi sigma square plus log e over 2 sigma square, and we know that this is a definition of your mean square value. Mean square or sigma square we have defined as integration sigma x square p of x dx. So this with the definition of your basic the probability terms. All right, so therefore this gets simplified as h of x, which can be written as half, okay, log of sigma square gets cancelled, so half exists in both the logarithmic terms, and hence I can write this as log of simply 2 pi sigma square into e. Okay, log a plus log b is log ab, right? So with that I can write, or I can find, I can find out the value of 2 pi times e, where e is Napier value e, so that h of x can still be written succinctly as a logarithmic of, this will come out to be around 17.1 sigma square. Okay, so this is the maximum entropy for a Gaussian distribution for a given mean square value. Okay, the above equation represents the maximum entropy for a given mean square value. Mean square value sigma square, and of course the distribution is Gaussian. Okay, okay, maximum entropy which will give for a Gaussian distribution. Okay, so we can also find out the maximum entropy for some given maximum value, where we have taken for two cases where we can find out the maximum entropy either at the maximum value of x or for a given mean square value of x. Okay, so if you can take the first part here, it can be shown that, okay, for a given peak value where x say supposedly varies from minus m to plus m, then maximum entropy is when x is uniformly distributed, very similar to your discrete random variable. Okay, where p of x is a power density function for a uniform distribution. It's 1 over b minus a, which is 2m when x is less than m and 0 otherwise. Okay, this can also be proved very similar to the case with for a given mean square value. Okay, so this is the one case where we can have another case for defining the entropy of a band limited white Gaussian noise. Okay, this will also, the result of this will also help us in defining channel capacity. Okay, so band limited in the sense we have given for a given channel bandwidth with where the noise is assumed to be white and Gaussian. White Gaussian noise is that noise where the power spectral density of the noise is flat, in the sense for all the frequencies irrespective of the frequency, the power density function is constant. So that we can consider Gaussian noise, consider Gaussian noise n of t, okay, with power spectral density as n naught over 2, where the power spectral density of a white Gaussian noise is flat. So for all frequencies, I can say Sn of f, which is power spectral density, is constant with a magnitude of n naught over 2. Okay, so that I can define, or I can find out the autocorrelation function or n of tau, which is inverse Fourier transform of Sn of f, by the definition of inverse Fourier transform, we can find that this autocorrelation function is given as n naught times b times sinc of 2 pi b tau. Okay, so where tau is the crossover value, how where a sinc is crossing over x-axis, where tau is integral multiples of 1 over tb, where k is an integer. B is the bandwidth of the channel. Okay, okay, so that therefore since sinc of 2 pi b tau is 0 for k plus or minus 1, plus or minus 2, and so on. Right, for all integer values, the sinc function crosses over the x-axis with amplitude 0. So this implies that even the autocorrelation of Rn of tau, which is in fact expectation as per the definition of the autocorrelation function, which is expectation of n of t times n of t plus k over tb at any other integer value or k over tb, this would give me a value 0, okay, at k plus or minus 1, plus or minus 2, and so on. Because of this fact, the Nyquist samples of all these n of t or the noise will be uncorrelated. So therefore, I can say that if I try to take samples of all these noise, therefore Nyquist samples of n of t are uncorrelated. All right. So since n of t is Gaussian, we can say that uncorrelated implies independence. Okay, each of the samples in n of t are independent of each other. So therefore I can say that Rn of 0 at tau t is equal to 0, we know that sync will have the maximum amplitude with an amplitude of unity, and hence Rn of 0 would be simply n naught times b, because of the fact that sync at tau is equal to 0 is unity. Okay, hence the variance of each sample, where we know that the autocorrelation Rn of 0, this implies the variance of the noise, which is actually Rn of 0 is n naught times b. And substituting that, therefore, since we have defined the entropy h of x for a given value of mean square value, for a given value of variance, h of x is nothing but, we have defined this as 1 over 2 log of, by the in general definition, where we have defined it as 2 pi e sigma square. This will become 1 over 2 log of, okay, 2 pi e n naught times b. Okay, so this is the maximum entropy or the entropy for a given value of the variance or the mean square value. This is with respect to the entropy of a band limited white Gaussian noise. Okay, so because n of t, which is the noise, is completely specified by the Nyquist samples when they are taken at twice of the rate. Okay, we can say that the entropy per second can also be defined in this fashion. Okay, since n of t is completely specified by, since the rate is twice of the bandwidth, by 2b Nyquist samples, okay, per second. Okay, because this is the entropy, this is bits per sample. Okay, bits per symbol or bits per sample in this case. So if I take the per second, I'll have to 2 bit of Nyquist samples. So this implies that h of x is simply half of log 2 pi e n naught b times twice of b bits. Okay, so therefore I can say that this, I'll give a new representation as h dash of x. This will give me a final result as 2 pi e and not b. Okay, so this will have units of bit per second. We will utilize all these parameters where the takeaway point from this discussion in this session is that that entropies that we define in for continuous random variables, these are the, I'll just try to list down those 2 points so that the summary, the takeaway from this session is that the first point is that h of x is differential or relative entropy. Okay, that's the first important point that needs to be understood properly. The second important point is that for a given variance or mean square value, for a given variance, okay, I can say that for a given variance, as we have defined so far, for a given variance, maximum entropy will be maximum, entropy is maximum when p of x is Gaussian. Okay, and that h of x, the maximum entropy, is defined as half log 2 pi e sigma square. Okay, so these are the two important points to take away from this session. For a couple of next sessions, I will define mutual information for a continuous memoryless channel, and hence it gives us the definition of the capacity over a continuous memory channel.